Stan Gibilisco here with a little explanation of the difference between phase shift by 180 degrees and phase opposition. In some waves, those two phenomena result in the same effect, but not always. What we're looking at here is a sine wave, time on the horizontal axis, amplitude positive going up and negative going down on the vertical axis, and this is a typical sine wave. Now let's see what happens when we move one of these waves by 180 degrees. There are actually two of them superimposed on each other right now. One of them's red, one of them's green, and the green one is on the top, and it's dominating, so let's move one of them. I don't know which one we're going to end up moving, but let's move one of them by a half a cycle. We'll move it 1/2 of a cycle later in phase. Now we have the red and the green waves, and they appear to be precisely out of phase with each other. That is to say, 180 degrees difference in phase. This cycle starts at the zero and positive going point, then a half a cycle later, the other wave starts at its zero and positive going point, and the frequencies are the same. In order for phase difference to have any meaning, the frequencies of two waves have to be identical, and therefore the wavelengths are identical, the periods are identical. So that's what happens when we move one of the waves 180 degrees in phase. If we move it another 180 degrees, we come back into phase. It's just that there's one cycle difference, but the waves once again align with each other, and that's what we get. Notice now we can determine the instantaneous amplitude at any given point of the composite of these two waves by moving this purple dashed line and then looking at the points where the purple dashed line intersects either wave. If those points are equidistant from the time axis, but one of them positive and one of them negative, then they will cancel each other out and we'll get zero. So at every point along here, that's what happens. We always get equidistant intersection points from the time axis on either side, and they always add up to zero. So when you have two waves that are different in phase by 180 degrees, sine waves, identical in frequency and identical in amplitude, they will perfectly cancel and you will get nothing. You'll get a composite signal of zero. Well, let's move these back into phase with each other now. And then, instead of moving one of them by 180 degrees, we will simply invert one of them. Now we've just turned one of them upside down. Now that's called phase opposition. There's a difference between a 180 degree phase shift, which is moving it horizontally in time, and phase opposition, which is flipping it upside down so that every positive becomes negative and every negative becomes positive. But notice, with a sine wave, the net effect of phase opposition is just exactly the same as the effect of a 180 degree or half cycle shift in phase. The intersection points are always equidistant from the time axis, and therefore, because they're on opposite sides, they always add up to zero. So in this case, with a sine wave, two sine waves in the same amplitude, the same frequency, if we have phase opposition, we will get the exact same effect as we get if we shift by 180 degrees in phase. But now, let's take a look at a sawtooth wave instead. Now again, we have two superimposed sawtooth waves. The cycle begins right here, zero and positive going. The next cycle begins right there. So let's take and move one of these waves by a half a cycle, shifting it by 180 degrees later in time, and then we can look at the instantaneous amplitudes. Now here, interestingly, the instantaneous transition here is meaningless for the purpose of determining amplitude. Actually, right now, at this point right here, the amplitude is at the positive peak. So we see, let's move along a little bit here and see what happens. Now, notice the two waves do not exactly cancel because the red wave intersects this vertical line somewhere above the axis. This other wave, though, will also intersect. Let's move a little further along down and check it out. Okay, I stand corrected. We have, let's see, we have two different waves on opposite sides of the time axis, but they are not equidistant. Notice that. Here, the red wave intersection point is farther from the time axis, indicating a greater amplitude, and the green wave is not as far, indicating a lesser negative amplitude, so the midpoint between them is somewhere up around above the time axis like that. They do cancel at certain points, like right here they do, but here notice they don't, and they usually don't. So we're not going to get complete cancellation of these two waves when we move one of them by a half a cycle. So now let's move it back and let's try phase opposition. That means we simply invert one of these waves like that. That looks quite different, doesn't it? Quite a lot different now than what we had when we shifted by 180 degrees. So a sawtooth wave does not behave this way at all. With phase opposition, we generally will always get cancellation, no matter how complicated or esoteric the wave. Notice equidistant points intersecting that purple line. Wherever we move that purple line, the red wave and the green wave intersected at equidistant points, but opposite sides from the time axis. So we always get cancellation, and the net result of this wave is 0. They cancel completely. So the situation is phase opposition and 180 degree phase shift are not the same phenomenon with a sawtooth wave, but with a sine wave, no, I don't want to save it, doggone it. With a sine wave, they are the same. So when you hear the terms 180 degree phase shift, oops, let's try that again. When you hear that term, and then you hear the term phase opposition, these two phenomena are theoretically different. They sometimes have the same net effect, but not always. In fact, usually not. The sine wave here is a very special case. Stan Gibilisco signing off. Back to intergalactic space, where arguably I belong. Until next time, so long.